course we will be discussing here, that is on parallel algorithms. Okay. Now the parallel algorithms is an algorithm which you will be designing on parallel machines. So before we discuss about the parallel machines, I think that it is first I have to tell about that what is sequential machines and sequential algorithms and the sequential data structures, what is the other issues involving that. Then we'll discuss about the parallel algorithms. Now, prerequisite of this course, what we expect from you that you have the preliminary knowledge on data structures, and algorithms. Now this data structure and algorithm, these two words are completely linked to each other, and they are covering a very small component on that software engineering cycle, life cycle. Now what is algorithm? Algorithm is a step-by-step procedure to solve a problem by an automaton. What is automaton? Automaton is nothing but, I can give you one example. Suppose your mother has told you to bring some item from the market, say brinjal. And you have gone to the market and you have found that brinjal is not available in the market. What are you going to do? One way could be, possibly you will not be purchasing anything and you will be coming back without thinking much. And this is that you have acted as an automaton because you did not use your brain to think that what will happen if brinjal is not available at home, and then possibly you will not be able to get your food. So idea is that you are not using your brain to solve this problem. So you have, that is that an automaton is a machine who does not have any brain to think. So that is the definition of algorithm. Now what happens in the algorithm? So we have few things in your mind that it must terminate after some time. Otherwise, that will be an infinite loop and you will not be able to decide whether your algorithm gives you the correct thing after a certain amount of time. The next problem is that algorithm must be definite. That is, that there should not be any runtime error or something undefined material exists in the steps. And third factor, one should keep it in mind in the case of algorithm that it must be an effective. What does it mean? That if I use pen and pencil, I must be able to solve every step of the algorithms. But it may so happen that it may take huge amount of time to solve the problem. That may be a possible scenario. Now another factor you should keep it in mind in the case of algorithm, there must exist some output. Otherwise, what for you are designing the algorithm? If you are not getting any output or you are not using any output, then this algorithm does not have any meaning. No, there should be some input. Every input is internal one or external one. Now, based on that, you can design the algorithms. Now, the thing is, the algorithm is dependent on data. Now, it may so happen that you have different sets of data, and now how you are arranging them, that is known as data structure. Now, an algorithm can be suitable for one kind of data structure, but it may not be appropriate for another set of or another type of data structure. So there is a highly link between algorithm and data structures. So basically, the meaning of data structure is that the way you are arranging the data is data structure. Now there are certain operations you perform on data structure. One is that you want to read the elements. Another one is that you want to modify certain elements. Another one is that you may like to insert some elements or delete some elements from the data set, or you may reverse, or you may perform certain operations or modification on some elements on the set of data, right? So these are the few operations we like to perform on data structure. Now, and a data structure or a type of data structure may be suitable for some type of operations, may not be suitable for another type of operations. So while you define the data structure, the programmer or designer must think about that the type of operations you would like to perform on the data. Depending on that, you design, or one should design the data structure. So once the data structure is defined, then only you can think about to design the algorithms. Once you design the algorithms, what are the factors you should keep it in mind? One, the algorithm must be correct. Until unless the algorithm is correct, you cannot justify that this will produce the result. Now, once you know the algorithm is correct, then the question is coming that the algorithm must be efficient. Now, what do you mean by efficient? Efficient means that it must be able to take less amount of time to produce the result. Another possibility is that it is taking less amount of space so that it is not loaded on the computer. However, nowadays the space problem is not that difficult, because it is easy, or the cost-wise, the getting memory is not very costly. So we do not consider that space factor much for designing the algorithms. But of course, computing time plays a major role to define or to design the efficient algorithm. So there are two types of complexity. One is known as time complexity. The other one is known as space complexity. Now, how to measure the time for an algorithm? One way possible way is that you design an algorithm and then implement it on some machines, and then you tell how much time it takes, right? So, but this is completely machine dependent, and in order to compare one algorithm with another algorithms, then you need to get that algorithm and you have to run on the same machine, and then you will be able to tell which one is better with respect to time. Now, another factor is that while you tell that my algorithm takes X amount of time on then you have to specify the type of machine you have used, which is changing day by day. So that is not a good way of measuring the time for an algorithm. So next factor could be that you can tell the number of operations you are performing on algorithms, and for each category of operations, the number of each category of operations, number of times that operations you have performed, right? So number of operators you have used, and for each operator, number of times you have used, that you can compute, and then you can estimate the time, because you can tell that for multiplication X amount of time, for addition Y amount of time, and so on. So you can compute the total amount of time needed for algorithms, or for these algorithms. But again, this is also not an easy task to estimate or to find out the number of operations you are performing in an algorithms. So what is the different way of estimating the time for an algorithm? One possible thing is that the number of, you for an algorithm, we can find out which are the operations are critical. Say, for example, in the case of sum of n numbered, addition is the critical operations. In the case of matrix multiplication, multiplication is the critical operation. In case of sorting, comparison is the critical operations. Now, the number of operations for that problem can be defined in terms of input-output parameters. That is, the number of inputs or number of outputs you are generating that can be used to estimate the time complexity. For example, that suppose I have n elements and you want to find out the sum of n elements, then the operation, number of operations or the number of additions you will be using is a function of n. Is a function of n. Can you estimate the number of, or can you tell me the number of additions you need to find the sum of n elements? Yes, the number is n minus 1. Number is n minus 1 additions you need to find the sum of n numbers. So that is, the number of operations is known as n minus 1. So this is the dependent on the input parameter n. Similarly, in the case with multiplications or matrix multiplications, here classical algorithm could be for I equals to 1 to n, for j equals to 1 to n, Cij is equals to 0, for k equals to 1 to n, Cij is equals to aik star bkj plus Cij. Right? This is a simple classical algorithm for matrix multiplications, and you observe that here the two types of operations you have used. One is plus, another one is multiplication. Now you know the multiplication is the costlier. Multiplication takes more amount of time than addition. So the critical operation C is here is multiplication. You observe that if I see whole algorithms, then two assignments or assignment statements, one addition and one multiplication. Besides this loading of this assignment for this for loops. Okay? And here this multiplication is a critical operations we are assuming, and the number of multiplications you need to find the matrix to compute the matrix multiplication is this one, which is NQ. Okay. So again you observe that time complexity. So the time complexity we measure using the input-output parameters. Now here you'll find that the worst case possible and the best case possible. So for example, to sort n elements, you may find that sometimes that worst case environment is this, and sometimes you may get the best case environment. So in the case, in order to estimate the worst case and the best case, we use these two notations. This is known as BO and this is omega notation for best possible, that is the lower bound, and this is known as upper bound. This is known as lower bound. Then we have another notation which is known as theta notation. And the small o notation. Now what is the big O notation which you use for worst case time complex? Fn be a function of x. Let Gn be also a function of n. Then we tell Fn is of Gn. We tell Fn is of equals to big O Gn if there exists a constant C and N naught such that Fn is less than equals to C times Gn for all n greater than equals to n naught. Right? Fn is of OGn if there exists a constant C and N naught such that absolute value of Fn is less than equals to C times Gn for all n greater than equals to n naught. Say for example you have a polynomial of degree n, say Fn is En x to the power n plus n to the power n minus 1 a1 x plus a0. This is a polynomial of degree n. Agree? Now, if it is a polynomial of degree n, what does it mean? That en must be, this is the leading coefficient which must be not equals to 0. So, suppose I want to find out the worst case time complex or worst case complexity of, I can find out by this is less than equals to en plus an minus 1 a1 a0 to 4. Agree? Now an minus 1 a1 a0 they are constant, so I can write c times x to the power n. One thing you have to keep in mind, if I can write only this is less than equals to this, provided they are all positive positive numbers. Otherwise, I should write this is n plus 1, and then I have to write here n plus 1. Agree? So if it is the case, so I can write this is O x to the power n plus 1. I have for I equals to 1 to n, for j is equals to 1 to I, and you have sums. Now suppose I want to compute the complexity, worst case complexity of this algorithm. So you will be writing that summation over I equals to 1 to n, summation over j is equals to 1 to I, and you will be writing, say, for 1. So this can be written as summation over I equals to 1 to n, and this is becoming summation over j is equals to 1 to y, c. C is constant. So this becomes summation over I equals to 1 to n, c into y, and which gives you c into n plus 1 divided by 2. Agree? So if it is the case, c into, so can I write this is equals to c into n square. C equals c into n square. Now, for what value of n this will be true? So let us assume n equals to 1. N equals to 1, the result is 1, and n equals to 2, the result is 3, and so on. N equals to 2, result is 3. So I can write this is true for n greater than equals to 1. So this I can write, this is an order n square. Order n square. Now can you tell me, can I write instead of order n square, can I write order n cube? Yes, answer is yes, you can write, because I can always write summation 1 I equals to 1 to n, j is equals to 1 to y. This is less than equals to c into n square. This I can write d into n cube plus c into n square, where d is 0. Now, if I assume that no c plus d n cube, and this is always true for n greater than equals to 1, and this is equals to e into n cube, where e is constant, so it is order n cube. Now see, you observe that this order n square is so that I can write order n cube, but problem is somewhere else, because I have to sell my algorithm, I have to tell that my algorithm is efficient. So in order to do that, I have to see that this is as close as to the lower possible values. So which is order n square. Now, I have a small question for you. And the same, where b and a are the constant, order log b n, whether is it equals to order log a, and where a and b are the two constants. Suppose I want to prove that they are constants. So can I write this one, order log b n is equals to less than equals to c times log b n, that is equals to c times log b a log a n. So this is nothing but d times log a n, where d is constant, so I can write order log a. So while we tell about the complexity, we don't mention about this base of logarithm, because it doesn't have much meaning, doesn't have any meaning to define the worst case time complexity. Now think about the other symbol, which is known as big omega symbols. Here it is that it is talking about the lower bound, which that means that you have fn and gn are the two functions on them, and you have the two constants d and n1, and here it is fn is greater than equals to c d times gn for all n greater than equals to n1. In that case, if it is the case, we tell fn is omega g. That is, it tells that if I tell fn is omega of gn, that means that it has achieved the lower bound with a constant factor, within a constant factor. Now theta is another notation we use where you can have the two functions fn gn and hn. We tell fn fn is of theta gn if b times gn. Right? That means that Fn is achieved in both lower bound and upper bound of the elements, right? In the constant factors. So we introduce the notation theta for this purpose. Now there is another notation we use, asymptotic notation, O, small o. Small o is used for asymptotic. That is Fn is small o gn. That is asymptotic to, Fn is asymptotic to gn if limit enters to infinity, Fn gn. Right? So we tell Fn is asymptotic to gn if limit enters to infinity, Fn by gn is equals to 1. So these are the terms we used for sequential algorithms, for evaluating the sequential algorithms. Now let us discuss about the data structures. You have done something in your undergraduate course, and first thing is that you have done the simple data structure which is known as the array. Now once you have an array, you have to tell the a priori what is the number of elements in the array, right? So array of n elements. And so the first part is that it is known to you the number of, or you have to declare a priori the number of elements in the array. That is the major disadvantage on array. Now the second thing is that let us try to perform certain operations on this array. Suppose I want to read the elements in the array, so you need to read all the elements one by one, and that takes order n times. Agree? Now once these array elements are read, then at any moment you can fetch the ith element in order 1 time. So reading the array, reading whole array takes order n time. Once it is read, the reading the ith element in the array takes order 1 time. The next one is that suppose I want to insert an element in the array. So this insertion is not an easy task in the array. Suppose I want to insert an element here. What you have to do, you have to get a place for this element. So in order to get that, all the elements has to be shifted by one house towards your right. Agree? So in the worst case, the insertion takes order n time. That is in the worst case. But suppose I want to insert an element here, then you don't have to do any shift operations, which takes constant amount of time, which is the best possible case. Now if you think about the deletion, what happens? Suppose I want to delete this element. Suppose I want to delete this element. Then you observe in order to delete, basically you cannot just delete it. So you have to bring this element here, this element here, this element here, and so on. So again, deletion also takes order n times, right? But if in the best possible case, suppose I want to delete the last element, then it takes constant amount of time. Now suppose I want to modify the ith element of the array. How much time do you need? Yes, it takes order 1 time, because I will just go to the ith element, and because it is a random access thing, so I can easily replace the content of the ith element, and which takes order 1 time. So these are the major steps or major operations you perform on each data. Okay. Now a simple question for you. You know what is the transpose of a matrix, agree? Transpose of a matrix is very simple operation it looks, but it is not while I try to write an algorithm. Transpose of matrix is nothing but that is you have Aij has to be interchanged with Agi. So that is the operations you are going to perform. It looks that is a simple, just you interchange between these two elements, you get it. But if I tell you the right hand algorithm for obtaining the transpose of a matrix, you will observe that it is not that easy. Let us try to understand. Can you tell me what I should write? Yes, for I equals to 1 to n. Then for j is equals to temp equals to Aij, Aij is equals to Agi, and then you will be writing Agi equals to temp. Agree? So if it is the case, now can you tell me what I should write here? 1. Let us see what happens if I write 1. Are you going to get the transpose of a matrix? Answer is no. It will give you the same matrix again. This is because of the fact that, yes, while you will be first times, you will be interchanging Aij with Agi. Again, when I equals to j and j equals to y, you will find that Aij has been interchanged with Agi. You will try at home and you see that it is 2 times interchange, and as a result it goes back to the original position, so you get the identity matrix. So what I should write here? One way that I can write I to n. In that case, yes, you will be getting 1 time interchange, and you get the transpose of the matrix. Yes, there is one problem here. You observe that if I write I to n, the issue is the diagonal element will be interchanged again and again. But there is no question of, or there is no need of interchanging diagonal elements of the matrix. So one can write I plus 1 to n. Right? Now suppose I want to obtain the complexity of this algorithm, then you can find out that I equals to 1 to n, j is equals to I plus 1 to n, and it is constant time, because constant time, so it is, and which I can write summation over I equals to 1 to n c times n minus I, n minus I, which I can write c n squared minus c times n into n plus 1 divided by 2. which is C squared, which is equal to U squared. So one thing you remember, the transpose of a matrix takes order in square times. That is the minimum requirement or minimum time. This is also the lower bound. Now the next data structure you have been taught, you were taught is linked list. Agreed? Now in the linked list, you know one is single linked list. Next one is doubly linked list. And then generalized linked list. Remember this? Yes. Now in order to discuss about the single linked list, so we have the term as node. Each node is having at least two fields. One is known as data field. Another one is known as link field. So data field, link field, and link field points to the next node. Okay, and the starting node is named as the name of the linked list. And here, if I have to perform operation on this linked list. Let us see what happens. Suppose I have to read all the data, so you have to read one by one, which takes order and amounts of time. Now, suppose I want to get the ith element of this linked list, then you have to traverse from the beginning to the ith position, which takes order I times. So, basically, you need order n times in the worst case to know the nth element of the linked list. Suppose I want to modify the nth element or ith element, then I have to go up to ith position and then modify that, which takes order I times. Now, what happens? The insertion and deletion. If I don't know which one to be deleted, or I know that it is the ith node to be deleted, I have to go to the ith position and then to perform the deletion operations. So it takes order I time to reach there, and then you have to perform the operations. Similarly, if I have to insert some node here, so again you have to reach up to this one, and then only you will be able to insert it, right? So let us assume that this order I time is still there, plus the insertion or deletion time to be considered, right? Now, let us see, suppose I want to insert a node after x, the node x after x. What I do? I arrived up to this by some means or some time, and then I will get a node, fill the data, okay, and then if I link this one first, then I lose the information about this one. So what I have to do, I have to link first this one, and then you will be linking this one. So link will go, this link will be out, so this will be the chain, so which takes constant amount of time. Now next one is, so this takes constant amount of time. Now suppose I want to delete the node after x. How can I delete the node after x? In order to delete the node after x, what I can do, I will put just the link of x to the link of the next node of the link, right? Link of x will be pointing to the link of x of link, right? That you know, which takes constant amount of time. Now what I want to ask you, the question is different, because up to this you have done in your undergraduate course. Suppose I want to delete this node. How can I delete this node? Can I delete it in constant? If I can do that, there will be a, so can I delete this node in constant amount of time. Yes? Is it difficult? Let us understand how we can do it. Say instead of deleting this node, because I cannot go back. So one way could be that I copy this data here, and then delete this node. In that case, copying takes constant time and deleting this node takes constant time. So you can delete this node in constant amount of time. Now think about the problem you face in the single linked list is that going backward is very difficult. Going backward is very difficult because you have to start from the beginning. So in order to get rid of that, we define the doubly linked list. Now, doubly linked list is that it has one is left link, another one is right link, and this is the data fit. What it does, that going backward or forward will not be a problem in the case of doubly linked. Another data structure you have done, which is known as stack and queue. Right? Say one example could be in the library you have seen that books are piled up one after another. Then the bookkeeper brings some books, again he piles on the top. And in the meantime, you are asked to read a book. So what are you going to do? From that stack of books, you will be removing one by one, but that's done from the top, right? Say for example, in the dining area of your hostel. So while you enter in the dining hall, you will find that the plates are stacked on the one on the top of another one and so on, and then you arrive. Right? You want to take your food, so you will be taking the plate from the top. Again, if the washman of that dining area, he got set of plates and he will be putting on the top of it. So that is an example of stack. Okay? But the example of the queue is very simple. You stand in the movie hall to get the tickets, the front person gets the ticket, he leaves, and then the person joins to get the ticket, he stands at the end of the queue. Now, let us understand what happens in the stack. Elements are like this. Now, suppose I want to insert an element. In the case of stack, insertion will be on the top. Suppose I want to delete an element, the deletion also will be from the top. And every time it takes the constant amount of time. So, in the case of stack, insertion and deletion from one end. In the case of queue, this is like people are standing. So another person comes, he will be standing at the end, and the person coming out will be coming from the front side. Right? So insertion will be one end and deletion will be from another end. That is the definition of queue. See, an example for this stack could be that subroutine calling. So you have a main program and you have a routine. Here you are calling subroutine A. Then you have subroutine A. You are calling the routine B. E is here. You are calling C. And then C is calling here, suppose. So here you have the return statement. This is the return statement you have, return statement, and here you have a statement. So what happens? While he gets the call A, so the system resolves the next statement, address of the next statement. So say next statement say yes, the address is yes. Now it goes to this one and now compute it, and he gets the address of the next statement of B, which can be T. So he stores T. So he gets the call B and he gets C and can be U in the next statement of C. So here it is stored here U. Now it performs the C. Now return, as soon as return statement goes, now he has to come back to the next statement of C. That is, the address is available in the stack, which is U. So he pops up that U and he comes here. He gets this return statement. Now he has to return to the state procedure A and he gets the return address which is T from the stack. So he comes here, then he gets the return statement. He has to come back to the main routine whose next statement to be executed, which is address whose address is S. So pops the S and he comes here and completes the job. So that is the one example where stack is used. You have used, or you know the term tree. What is tree? The next terminology we'll be discussing the binary tree. Okay. TT contains n nodes. N is at least one node, and one node is known as the root of the tree. Root of the tree. This is a specially designated node, which is known as the root of the tree. And suppose this is this, and you have the remaining n minus 1. They are connected to root node R. They are connected to the root node R. And also these n nodes form a tree. Form trees, subtrees. Okay? This n nodes forms X or P subtrees. Okay? So tree is basically, you have a root node R, you have a root node R, under that maybe some other root node. So if I remove this, then you get X disjoint subtrees. If I remove this, you get again some number of subtrees and so on. Only condition is that there will be at least one node in the tree. Now in the case of binary tree, empty binary tree is a empty binary tree is also binary tree. There is nothing in there, so that you can define what is binary tree. Otherwise, there is a specially node designated which is root node, and it has at most two subtrees. One is known as left subtree, another one right subtree. Left subtree and the right subtree. And left subtree and the right subtree, both of them are binary. Okay? You have the root node, left subtree, root node, and it has at most two children. So the left child, if exists, is the root of the left subtree. Right child, if exists, then it is the root of the right subtree, and each of them is a binary tree. Each of them is binary. Can you recollect what is heap? Heap is a complete binary tree. Now what is complete binary tree? Complete binary tree means that it is full up to the last but one level. It is full up to last but one level, and in the last level, it is full from left to right. Okay, so heap is a complete binary tree of level L, and it satisfies certain properties. One property is, in the case of min heap, this is the minimum element, or this element is smaller than both the elements of left and right child, and also this is left subtree is a heap and right subtree is also a heap. Okay, so this is a complete binary tree, and this node contains, in the case of min heap, this contains the minimum element compared to this tree, compared to its right child and left child, and left subtree is a min heap, right subtree is also a min heap. Graph we define G by the two terms V and E, where V is the set of vertices and E is the set of edges. V is set of vertices. Suppose you have n vertices, they are defined as V2, V1, V2, Vn. And you have edges, say E1, E2, E3 and so on, number of edges. And EI is an edge between VK and VL. EI is an edge relation VK and VL. Right? This is a possible graph where you can have V1, V2, V3, V4, V5, V6, and so on. Right? And we can tell tree is also a graph. Agree? Now can you tell me what type of graph it is? Tree is a cyclic graph. Now if tree is a cyclic graph, can you tell me the number of edges you have in the tree? Yes? If you have the n nodes, the number of edges will be n minus 1 in the tree. Because it is a connected acyclic graph which needs n minus 1 to maintain the connectivity. And if I add one edge, then it will become the cyclic graph. So that is the all this graph tree, and just we are defining so that while discussing our parallelisms, you don't face much problems. Now let us understand a simple problem and see how we can solve it. Now can you do you remember that how to find out the minimum of n elements? Or suppose you have n elements, and I want to find out the minimum of these n elements. One possible way is that you have A1, A2, An, and initially you define minimum is your A1. Then minimum is compared with A2. If you find A2 is smaller than min, then min is replaced by A2. And then you compare again with A3. And if you find that A3 is greater than min, don't do anything, go for the next one and so on. So in that process, you need n minus 1 comparison. find out the minimum of n elements. Now the problem is here, suppose instead of finding the minimum of n elements, I am interested to find out the second minimum. Second minimum. Now you tell me how can I find out the second minimum of this n element? So one possible way is that you first find the minimum. Now you have the remaining n minus 1 elements, and again you find the minimum. That will be your second minimum. So for the first case you give n minus 1 comparisons. Second time you give n minus 2 comparisons. So you get 2n minus 3 comparisons to find the second minimum. But is it the best way to do it? So let us consider this problem, that finding the second minimum. At this moment we discussed and we have seen that this many comparisons you need. And our target is to find out whether this is the best possible way of finding the second minimum. Now let us consider another problem. Suppose I am interested to find out minimum and maximum of n elements. Now, one way possibly that you find the minimum of this, which takes n minus 1, and again you find the maximum, you get again n minus 1. So, to find the minimum and maximum of n elements, you need 2n minus 2 comparisons. Right? But is it the best way of doing it? Answer is no. In order to do that, let us understand the scenario. That you have A1, A2, A3, A4, A5, A6, A7, and A8. Let us assume you have these 8 elements. Or for simplicity, let us assume that there are 8 teams are participating in one game, and we want to introduce the knockout tournament among these to find out who is the winner, right? So in order to do that, what we do, we divide into the 4 groups. Each group consists of 2 teams, and these 2 teams of each group play each other, and one of them will be declared as winner and one of them will be declared as loser. Okay? Now, in order to see the winner of this, so these 4 will be divided into 2 teams, 2 groups, and the winner is here. Winner of these 2 will be here, and these 2 teams will play each other and to declare who is the winner. Agree? That is the standard procedure to find out the winner of winner among these n teams by knockout method. Now replace W by min. What happens? So this gives you the minimum of these 2 elements, minimum of these 2 elements, minimum of these 2 elements, and minimum of these 2 elements. Now minimum of these 2 elements is here, minimum of these 2 elements will be here, and minimum of these 2 elements is the minimum of all these 8 elements. Agreed? So you observe the number of comparisons you have used here: 1, 2, 3, 4, 5, 6, 7. So 7 comparisons you have used. That is, you have used n minus 1 comparisons to find the minimum. Agreed? Now, in order to find out the maximum of this, you observe that maximum cannot be any one of them because they are the minimum. So maximum will be one of these 4 elements. Okay? Now one of the 4 elements means that you have to find out the maximum of these 4 elements, the 4 elements is nothing but that n by 2 elements, and finding the maximum of these 4 elements takes n by 2 minus 1. So the number of comparisons you need to find the maximum and minimum of an element is 3n by 2 minus 2. Agree? So it is much better than n by 2 n minus 2. Now what about the other one? That finding the, so if I look into this problem on tournament method, you get A1, A2, A3, A4, A5, A6, A7 and A8. And you have the winner or winner 1, winner 2, winner 3, winner 4. Then you have winner of these two, winner of these two, and then the W is replaced by minimum. Now suppose that this is your minimum elements. This is your minimum elements. So to find the second minimum, which are the probable candidates? This is a probable candidate, this is another probable candidate, and this is another probable candidate. Right? Because this is the winner of a minimum of these 4 elements, this is one case, and this is the minimum of these 2 elements. So you have that many possible candidates. Among that, you have to find out the minimum. So this you observe that every height gives one element. Every level you get one element. For this level this one, for this level this one, and at this level this one. The height of this tree is log n minus 1. Height of this tree is log n minus 1. To find the minimum, you get the n minus 1. Then height of the tree is log n minus 1. And to find the minimum of this, you get another minus 1. Height of the tree is log n plus 1, log n plus 1, so you get log n minus 1 comparison. So second minimum takes n plus log n minus 2, that many comparisons. So this is the serial. But remember, to find the third minimum, you cannot go further. You have to go one by one again. So which will become log n minus 2, then log n minus 3, and so on. So n plus log n minus 2 plus log n minus 2 plus log n minus 3, and so on. So you will find that suppose I have to find out the first minimum, second minimum, third minimum, up to n minimums. So this becomes order n log n. This becomes order n log n, which is basically nothing but first minimum, second minimum, third minimum, and so on, which takes that basically you are making the sorting of n elements, and which is the lower bound of this is order n log n, so which is matching with that. Today let us stop here, and the next class we'll be discussing about the different paradigms we use for sequential algorithms. And then in the third class onwards we'll be starting about the parallel algorithms and what are the things to be covered in the course. Okay? Thanks.